Finally, we'll get going. Oh, we're not getting going. Why is there no momentary pause while I try to see if it's not connected? Okay, I do not know why. Let's see. All right, so your suggestion was drag your presentation to the other screen. And I'm like, what are you talking about? What other screen am I going to drag my presentation to? I presume they mean this, but then I can't write. Anyway, they're going to come and undoubtedly tell me I did something wrong. Okay, so while we're waiting for that to happen, my apologies, I don't know why it's not on. Let's see, are there any questions? Let's go with that first. Any questions about what we've been doing? Nobody has a question for me. Okay, so let's just get ourselves in the place where we're going to be at. We have talked about numeric differentiation. We have talked about numeric integration, and now what we're doing is we're looking at the idea of solving a differential equation numerically. This is a huge endeavor, an important endeavor, used all the time. And so our idea, let's see. You're saying Okay, all right, no worries. Yeah. All right, we're back in action here. So here's where we're at. We've got a differential equation, which we are going to write like this. The derivative of the function, this is a first order differential equation. It's first order because we have only the first derivative. So what's going to happen is we're going to say that the derivative of the function, the derivative is equal to some function of an independent variable and the function itself. Okay, let's just get an example here. Y prime is equal to y plus t squared. There's a differential equation. You see that y prime, dy by dt, is some function of t and y. That's what we're saying. Okay, so over here is some combination of t's and y's, and over here is the derivative. This is a first order differential equation because we have the first derivative. Unsurprisingly, something that looks like this. Okay, something that looks like that, for example, that is a second order differential equation. Okay. All right, so what we're going to do, we're in the situation where we've got, at least at this place, we're until a couple of lectures from now, we're sticking with the first order ones. And what we're going to do is say, we understand what the derivative of the function is. It is this. And now what we want to know is, what is this? Right? Let me not use f, that might be confusing. What is the function? Explicitly, what is the function as a function of the independent variable? And just to completely reiterate, if we had this kind of a situation, we had this kind of a situation, we then said, okay, we can express the function as a, thinking of this as dy by dt, as a function of the independent variable. Okay. That's what we wanted. That is the exact solution. So now what we want to do is numerically be able to figure this thing out at a variety of different points, which we then can connect in a sort of dot-to-dot connector if we want to sort of see what the function looks like. Or we can calculate the function at any point that we want. We are not finding this. What we're basically going to be finding is like this: y at 0, y at some other number, is like this, y at 2. That's what we want. That's what we're going to do. We're not going to know this, but we are going to be able to say, okay, we don't know what the function is, but we're going to have an estimate of it at whatever points we want. If you do enough of those points, we can pack them all together and draw it up. Okay. So here's an example. Just to show you, this will come up on the final computing assignment. That is, we have different ways of doing this. In this case, in this little drawing here, just to sort of illustrate the accuracy and robustness issues. In this case, here we are solving Kepler's differential equation. Remember Kepler? For planetary motion. Actually, I have a colleague. I've actually graduated from here with a PhD. Her name's Gemma Laurent. She is at Pitzer College, so in California, teaching there and doing research. And I find it amazing. But she had a baby about 5 years ago, and she named it Kepler. The guy's name is Kepler. So anyway, that's his first name. Okay. So here we have Kepler's laws for planetary motion. And They are presented as differential equations, as you will see. And so you can do a numeric solution to those differential equations and plot that out. You're starting from some initial planetary position, you know where the planets are. You use the differential equations, you solve them numerically, and you plot it out. And this is that being done with a step size that we're going to see. That's what H is, and 4 different methods. Okay, looking at this, which one is lousiest? The first one is lousy in a lot of ways, and you're going to see this exact same. You're going to see this happen when you do the competing assignment. First of all, look at the trajectory that's being predicted. Okay, this is obviously lousy because at some point it looks like planets are just predicted to spin off and not be part of orbiting around the sun anymore. So far, we have not seen that happen, right? We're still orbiting the sun, right? So also it is the case, we have observed that we stay on the same track as we're going around. We don't tend to wobble around, or our orbit doesn't change. So that one is the worst from comparing with observation. This one is better. And then these other two are much better. They predict something that looks much more like what our practical experience tells us. The actual stability of the solar system is an actually very difficult problem to solve. So the idea to ask the question, okay, here we are, we have this many planets, and some of the planets have moons and some of them don't, and we're all kind of orbiting around. And then to ask the question, is it stable? Is it stable? Or in a million years or a billion years, some of the planets, will they be gone? Will all the other planets still be here? So this was actually a subject of intense research, and Poincaré actually really did a lot of work on this, and to understand what is the stability of our solar system is not an easy question, actually. Okay, all right. We are going to introduce just a little bit of theory before we basically look at this method right here, the explicit Euler method for solving differential equations. We got to rely on some theory in order for us to be able to do anything at all. And so what we're worried about here is existence and uniqueness. Like, no use wasting time if we don't believe there actually is a solution to find. Okay, so we need this condition right here. This guy has an unfortunate last name that is said in English. It's the Lipschitz condition. Okay, well, I can't help this. Okay. So he's German. Doesn't maybe sound like he does not shite or something in German, so that's fine. Okay. Let me just tell you what this condition is. It's a function. We got a function of 2 variables. You can see why it's set up like this, because that's going to be our dy by dt is equal to f of dy. So we're talking about this function here. That's what we're interested in understanding, some characteristics of that function. So that function satisfies Lipschitz condition with constant L greater than 0 in the variable y if absolute value of that's the condition right there, and that is for all y1, y2, finite.
and for all t in the interval that we want to solve the differential equation. Okay, let's look at this and see if we can sort of understand what this condition is. Has anybody looked at this and telling me, like looking at this, you're saying, okay, this difference has to be always less than or equal to some number times this difference. What is that telling you, really? Anybody stats on that? Yep. Exactly. That is exactly correct. This is basically telling you, it particularly were you to think of putting this over here, like that, and removing it from here. You're looking at this thing here. It's not the way we tend to write it, but that is the possibility. You're thinking of a difference between divided by this is in fact that is the secret part, and so that is close to what is the derivative. So it is telling you that the derivative basically remains bounded. So this is a stronger condition than continuity. Okay, but it's not a condition on the derivative. Like we're actually not saying the derivative itself. We're not saying that the function is differentiable. We're just saying that the derivative is bounded. Okay, so it's stronger than continuity and it's weaker than differentiability. So if you've got a differentiable function, you're golden, right? Then it's Lipschitz anyhow, and it's continuous, right? Okay, and we're gonna basically all of our functions are gonna be like that. Let's just look at what the difference is. So here's two drawings here. That's the absolute value function. And here's another function. I'll just draw it like this. There, like that. Now, one of these functions is differentiability. So we did not from that to the are these differential functions? You would go, no. Either one of them has a derivative of two. So they're not differentiable on their whole domain. Okay. Then are they continuous? Yes, both of them are continuous. If you want to look how you can draw without lifting your pencil. Okay, now one of them is Lipschitz and one is not. Which one is where? Okay, in which case does the derivative stay bounded as you get close to zero? Huh? The left one. You just imagine the derivative is existing at all of these points. And as you're getting close to here, the derivative on coming from the right is 1, and the derivative here is -1. The derivative stays bounded as you're getting close to 0. In this case, the derivative keeps getting bigger and bigger and bigger as we get close to 0, so it stays bounded. This guy is Lipschitz, this guy is not. Okay. We need our functions to be here. We do not actually have to be differentiable, but the derivative must stay bounded. That's what this condition is for. Otherwise, the whole thing breaks down. Okay, that is the reason why we're introducing this, just so that we can properly say the following: we're guaranteed a unique solution if the function continuous and that's it. Basically, all the functions we're dealing with are going to be like this. And this, if you'll recall, this means initial value problem. So we have this condition in place, and that there's our differential equation. There's the interval over which of the independent variable we're interested in having a solution on, and there is our initial condition. It is a first order differential equation. We have one initial condition. When we have a second order differential equation, like that, we will have two initial conditions. Like that. So whatever the degree of your differential equation is, for an initial value problem, you need to have two, that degree, that number of initial conditions. Okay. Then we have another vocabulary, well posed. Well posed means small changes in input, yield, small changes in output. Okay, so we're just gonna write that out in this condition. If we have an initial value problem, that initial value problem looking like this. Like that. So we have our interval. We have our initial condition. It is well posed. Well posed, if a unique solution exists. And two, or any epsilon greater than 0, sufficiently small. And if delta t is continuous, is a continuous function. If the absolute value of delta t less than epsilon. So this is your sort of jittering around, your noise, your small change to your input. And there is some other number, gamma, less than epsilon. The initial value problem. And this one, where we consider it like this, plus some small jittering to the input. We get, here was what the initial condition is. So we just slightly jitter the input. And if we do that, we want this guy to have the difference between the solution to this guy and the original guy will be less than some constant times epsilon for fixed constant. Like this k is fixed, so fixed k greater than 0, independent of epsilon. Okay, so this is just a fancy way of saying if you have some different condition, like what is the
some very small steps, and then you get a large size difference. This is the opposite. We want to keep this what we call a well-posed problem. Okay, now it turns out we're not going to prove this, sadly, but it does turn out, and you're right, this is a theorem without a proof, that is if f of ty is continuous and well, we have the side here, and Lipschitz, then the initial value problem is well posed. Then the I so practically speaking, what we want to do is change the input with small changes like this. How are we going to do that? Before we go ahead and try to make any more solution. That is just the function. This guy here. Where is he? This guy here. We check if this function satisfies the line between okay, any questions, comments about this? Move on to then trying our first method of solving a differential equation numerically. Okay. Yeah. You up here? Okay, here we are. We got the initial value problem. There it is. First order initial value problem for which we have one initial condition. What we want to do is approximate the unknown solution, y of t, at a series of points. They're going to be equidistant. Starting at the beginning, with the initial condition, like you notice how this is A and this is A. That is, we're going to start at the initial time. We can call it time, but it doesn't have to be time. And then we're going to move over in little increments of A. And we're going to predict the solution at all of those times. Those uniformly spaced points are called the mesh points. We are going to call the approximate solution W of I, and the exact solution is Y. So W of I is going to be approximately Y at Ti, for I is equal to 0 to n, which are our mesh points. This one, Euler's method is based on the forward difference formula. So we call that from what we did before, and that is the forward difference formula telling you that the derivative at a certain point can be approximated by the function at the next point minus the function at that point divided by the step size. And then we have the error back. So, okay, so what do we have? Now we have a differential equation, and the differential equation looks like this. The derivative at time Ti is some function of Ti as well as the value of the function at Ti. That's the differential equation right there. So now I write out what this is from above. I know what that is. Let's take this. That is y at Ti plus 1 minus y at Ti divided by 8 minus 8 squared over 2 times the second derivative times okay. All right. Now I solve. I mean, the way this method is going to work is we are going to start knowing the derivative at the first point.
And then what we wanted to, well, actually, let me backtrack on that. We're gonna start knowing what the function is at the first point, and what we wanna do is figure out what is the function at the next point over. So what I'm doing now is gonna solve this statement right here. Let me just, my color here. What I'm doing is solving this guy. Solving this equation right here. I'm gonna keep that in for a bit. I'm gonna solve that equation for this. Looks like this. Y at Ti plus 1 is Y at Ti plus H times F at Ti, Y at Ti plus H squared over 2. Okay, what is this guy right here? What is that? F at Ti, Y at, huh? Right, exactly, right here, this is Y prime at Ti. Okay, so we do the usual thing that we often do, and that is we now just toss out this error term, like toss this guy out. Now that's where the approximation happens, right then, and we obtain Euler's method. And it gives us an approximate solution for our differential equation. So we take the first approximation for our function to be the initial condition. I mean, we've got told that. This is the way by the time people here. We're like, hey, let's approximate that. Exactly, right? So we take that, our first approximation to be exactly our initial condition. We know that. And then we take our next approximation for the function to be the previous one plus h, the step size, times the derivative. That is Euler's method, right there. That is this right here. That is this right here with y, the exact solution, replaced with w, the approximate solution. This is called the difference equation from Euler's method. We're going to take a graphical example of what this is looking like. It's not actually that complicated. It's just a matter of keeping track of the things in your head and the nomenclature, and then realizing once you see graphically what's happening, it should be hopefully fairly straightforward. Okay, so let's just do this graphically. Okay, what do we know? We know the function at time 0. Okay, that is what has been called A. We know y prime at t0 is equal to f at t0, y at t0. And that's the difference. That's actually true for every 0, 1, 2, 3, like that. Okay, so what are we doing? We're here. We've got a differential equation. It has an exact solution. So this is the exact solution of the differential equation. We don't actually know that, but I mean, it does exist, so we've checked that. Right now, we want to approximate this guy. So what do? We're here, and we have some initial condition, which is given to us at time t0, the wave height at time t0. That becomes our first approximation. That one is exactly that. So that becomes w0. That is y at t0. Then we calculate, we estimate the derivative like this. Basically, we calculate the tangent. We're calculating the tangent line, or whatever. Great. We take the tangent line right here and that. We then move over to time t1. This distance right here is A. Right here, this number right here is the exact solution, y at t1. We don't know that. So what we do is, and we don't know what the function looks like, don't have a explicit description of a function, so what we do is we move along the tangent line and we get to right here. And we call that W1. That is W1. W1 is approximately y at t1. Sometimes we even write this y1. So that's our approximation right here. But the idea is not complicated. And then this is the exact size, which we do not know. Okay, now we proceed. We'll just draw this out again. We're going to proceed to the next step. Out of the step. We have the same exact function. Still don't know. Something like that. We do exactly the same thing. We start at 0. We take a tangent line. I'm going to enlarge this a little bit. Easier for myself to draw. We go T1, like that. We make this guy W0, and this guy here W0, just like before. And then now we're here. What do we know? Well, we actually know, okay, right here is y at T1. We don't know this. But what do we know at T1? What do we know? Pardon me? We do know the derivative, right? We don't know, so let's just write this out. We don't know y at T1. But we do know y prime at T1. How do we know that? Because we have the differential equation. Y prime of t is some function of t and y. So we can calculate is what y prime at T1 is. So we're able to then get this, slope right here. Okay? We don't, however, know where that is. We know this slope. So what we do is, and we're down here. So what we do is we make this line parallel, like that. We make this line parallel like that, and we go along and find T2. We're like, hey, this is our next estimate right here. That's W2. Okay, meanwhile, if I extend my function up, there. Meanwhile, this guy right here is actually y at T2. So W2 is now my approximation and y at T2. That's how this method is doing. And we do the same thing. Okay, just keep going like this. And you might be able to see from this drawing, of course, it depends on the underlying function is looking like, but it just keeps getting worse. That's why you're sort of predicting, oh, that's not too bad, but I would, as time goes on, you kind of lost it. I kind of like this to like this is the reason we have but that's the idea, right? I mean, what else can you do in some sense, like that would, only have access to the speed and direction the person is running at every, at sort of an interval thing, and you just adjust based on that, and you try to catch something. That's what this method looks like. Okay. The upside of this method, there are some upsides. You only got to do one evaluation, one functional evaluation per step. That's not bad. That's fairly efficient. We're going to see better ways of doing this in the sense that they're more accurate, but they will require more evaluation. I already stated this. Sometimes we simplify the notation in this way. And now we want to know like how accurate this method is. I mean, I think that clearly depends on how small the step size is. If the smaller step size is one, yeah. Yep. What is this line right here? This line is parallel to this line. This line right here is the derivative of my function at time t is 1. Well, which is what I'm allowed to calculate because I can always calculate the derivative. I have a differential equation, right? This is the thing. You cannot calculate the function, but you see, let me just maybe give an example. Like, let's just go like this. Y prime is equal to 2 y t. Maybe make it even, maybe make it like more obvious. Plus 3t. There's a differential equation, right? I then know that y at time 1 is equal to 3. Okay. All right. Yes. Okay. So here's the question. I'm going to finish this question, and I'll answer your question. Okay. So I'm here. I'm like, I get, this is my differential equation. This is my initial condition. Okay, so y prime at 1 is 2 times y plus 3 times t. That is 6, 9. Right? I can calculate the derivative. Now, if I want to calculate y prime at 2, that is going to be what? That is going to be 2 times y at 2 plus 3 times 2. And I just estimated this according to my scheme. I just estimated this, so I plug that in, and I get y prime at 2. That allows me to draw that line. You can always calculate the derivative. I have a differential equation. I can't calculate the function because I don't know the function. Now this guy asked me, why don't you just solve the differential equation and calculate the function? Right? Is that what you just asked me? Okay, so the thing of it is, so the question is, well, why waste time with this? Just integrate and tell me what the function is, and I can just make the calculations directly. And that is the exact solution, right? Absolutely. But the issue is, here, let me just, it's really easy to do this, okay? Here's a differential equation. No, you put that into Wolfram alpha. You won't get it, you won't get it, you won't get it. Right? Okay, question, now that is a better question than your first question, I agree. So it may be possible to identify the function so that it looks like this. Whatever, there's some stuff here, right? Whatever. I have no idea what this looks like for this thing. Yeah. Yeah. It may be possible, in fact, to find an individual solution, or as I'm going to probably tell you can't find it. Because there's no element you find this kind of time. Which point is the universal project to do? If that is possible, it may, however, not even be possible to make this step. right? And then you're where we are. It is actually much more typical to just numerically solve this directly than it is to attempt to make this step, because let's face it, this is also usually some sort of symbolic stuff, which is hard to do, right? So that is much better question, rather than revising question. Yeah, 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 okay, good. All right, other question. Okay. All right, so the accuracy of this slide depends on our step size. And what we want to actually know is we want to know, does the numerical method converge to the solution if you make your step size smaller and smaller and smaller and smaller? One would hope for that to happen. That's what this step is saying right here. A numerical method for solving a differential equation is called convergent if the error between the approximation and the exact solution goes to zero as the step size goes to zero. That's what one would hope for. You make little tiny step sizes. You should track it exactly. This is not just for Euler's method. This is for all types of numerical solutions that we might consider. That is the definition of university convergence. Okay. Suppose we got a well-posed problem. And I can then tell you, I'm just going to tell you, this is, the proof is in, here the proof is, I have it, it's page 271. But, so the Euler's method is convergent. If you make the step size small enough, you will be able to track the solution. That's a nice feature. And then the error bound here is written here. The difference between your exact solution and your approximation is bounded. And again, this is proved in the version there. And then the difference here between the ones we've seen is this little L. This is the Lipschitz constant. That's another new wrinkle coming into the program, right? It shows up a couple of different places. So, well, but it will just say here, Euler's method is not accurate enough to use in practice, but it is conceptually simple. So we're starting here. Not accurate. Practice. That's unfortunate step one. However, if it does have the design, simple enough, you can analyze the error. There's some upside to the simple method. Okay, when we make this error bound for the Euler method, it is often a large overestimate. So that's really the test, right? So I mean, this is just like, let me tell you something. Let me tell you. I have not. Getting a big overestimate is not that useful. Also, the bound that we have given has been a bound on the truncation error, right? We truncated that term on the numeric differentiation, right? We ignored the round off error. Okay, that error. What happens to that error when H gets it gets bigger, right? As H goes to zero, round off error increases. This is because we basically use the formula we use for numeric differentiation. So we sort of left that aside because the situation is now a little bit more complicated. And we just left that on. There's some amount of talk about that in the session. We talked about the global error of the method. This was over the whole range. Talked about that. That's often not, possible, given the complexity of the numeric method. So we're also going to, you will see the next class, we'll see the local error, where we try to estimate the error just close by where you're at. Okay, so that's our introduction to this. Be back on, Friday, we'll have a quiz, and we will continue with the solving differential equations numerically. Thanks, guys.